The problem I want to solve today is on the application of the second law of thermodynamics to a control volume, which is in fact a cylinder piston arrangement with some inlet flow. This problem has special peculiarities which, as we progress through it, I shall discuss that in detail. I've selected the numbers from a problem in the book by Sengel, which is a very good book on thermodynamics and has very good problems. Now, the problem is on a cylinder piston arrangement. So, if we draw a cylinder and piston, the problem would look like this. This is our cylinder, and there is a free moving piston in it. It means that as the piston goes up and down, the pressure does not change and remains constant. Now, the problem tells us that initially M1 equals 1.3 kilograms, V1 equals 0.4 cubic meters, and there is air inside this cylinder. The cylinder is insulated, so we just put some insulation around it, and note that Q would equal 0 in this problem. Now, the initial temperature is 30 degrees C, so T1 equals 30 degrees centigrade, which of course is equivalent of 303.15 kelvins. That's the number that we shall use in our calculations. So, it states that there is incoming air, so there is a point I, and the incoming air into this cylinder has a temperature Ti equals 70 degrees C, which equals 3.3.15 kelvins. That's the temperature, and the pressure for incoming flow is 500 kilopascals. That is 70 degrees C, and it is 500 kilopascals. So, the problem tells us that the incoming air would continue to enter this cylinder until V2 finally V2 equals 1.5 V1. This means that the volume inside the cylinder would be added by 50%. So these are our knowledge from this problem. We have no more information, and what, of course, it doesn't matter whatever the problem has asked us. What I would do is to just solve the problem and calculate everything that is possible. So, what are our steps to calculate the problem? We do these steps one by one, as usually we have done. The first step is to decide on the control volume. Decide on the boundary of interest. What are we interested to solve? And the boundary of interest is, as you may guess, it is just inside this cylinder, where there is one entry point and there is no exit point. That is the boundary of interest. The second step that we have to take is to calculate. So this is one. Two is to calculate the properties as far as we can. So the second step is to calculate properties. And for the initial condition, we have more information. We know that the perfect gas law tells us that P1, V1 equals M1 R T1. And in this equation, we know the volume. We also know the initial mass and initial temperature. So we are able to calculate initial pressure. That's how we do it. P1 equals initial mass 1.3 kilograms or 0.287 kilojoules per kilograms Kelvin, and T, which is 303.15 divided by the um, initial volume, which is zero point 0.4 cubic meters. All dimensions match, and since we have used kilojoules per kilograms here, we would gain kilopascals for pressure, and therefore P1 would equal 282.8 kilopascals, and this we would call P, which is also constant. It is constant throughout. Constant throughout. Since this piston is free to move. We are also able to calculate a specific volume. V1 equals volume, which is zero point 0.4, divided by mass, which is 1.3, and that would equal 0.3077 cubic meters per kilograms. This is the specific volume at initial condition. Now, moving from the initial condition, the other information we are given is about the mass that enters this control volume. And the information we could have is that Pi Vi equals R Ti. We don't know mass, and the volume is meaningless for a flow that enters, but the specific volume is, of course, a property that we could calculate. Therefore, Vi equals 0.287 times 343.15 and divided by 500. And the outcome for Vi, specific volume of the flow that enters this control volume, is 0.197 cubic meters per kilograms, and that is the flow that enters this control volume. Now, that's all we can know about the flow that enters, and now we can move to the final condition, which we know about it. For the final condition, we know that V2 equals 1.5 V1, and since V1 is 0.4 cubic meters, V2 would be 0.6 cubic meters. Also, we have P2, which equals P1, and that is 282.8 kilopascals. You see, look at a similar equation for point 2, and we know P2, we know V2, but we don't know M2 or T2. So the conclusion is that T2 and M2 are unknown. And that's all we know about the properties. Our next step should be to simplify the governing equation. So this is how the governing equations look like, and starting with the mass conservation equation, dmc by dt equals m dot I minus m dot E. And this is the change of mass inside our control volume, which if we integrate it between initial and final conditions, that would be m2 minus m1, and this equals mi, which has entered our control volume during this process between 1 and 2, and there is no mass that has left our control volume. So if I write it down, the simplified version of the mass conservation equation would be m2 minus m1 equals mi. This is the mass that has entered our control volume between conditions 1 and 2. Now we move to the energy equation, and the energy equation tells us that the change of energy inside the control volume, which would be m2 E2 minus m2 E1, and ignoring changes in velocity or elevation, m2 U2 minus m2 M1 U1, would result in the mass that has entered times its enthalpy. Ignore velocity and elevation. There's no mass has left, so this term is 0. The problem is insulated, so the heat transfer is 0, and we are left with work. Since the piston moves, then there is certainly some work which is done on the surroundings. The work is done on the surroundings since the volume has increased inside the cylinder. The piston has moved and it has done work on the surroundings. So the simplified version of the energy equation would be m2 u2 minus m1 u1, which is the change of energy inside our control volume, and this equals mi hi and minus w, which is the work. Now, the third step in this process is to see how the simplified version of the second law would look like. It is the change of entropy inside our control volume, which would be m2s2 minus m1s1. some entropy has entered our control volume with mass, so this would be MISI. No mass has left our control volume, so this term is 0. There is no heat transfer, and therefore this term is 0, but there is generated entropy. Why there is generated entropy? We have to look at the problem and see why there is generated entropy. Look, this is a 500 kilopascal mass air that is entering a cylinder which is at 282 kilopascals. So there is a pressure difference. The air that enters would expand through this pressure difference, and therefore this sudden expansion would be irreversible. So there is entropy generation. The second point is that this is 70 degrees and this one is 30 degrees. We don't know how the problem ends, but as it is, at least for the start of it, a 70 degrees C flow of air is entering air at 30 degrees C. So there's a temperature difference and there would be heat transfer. This air would warm up the air inside this cylinder. So there's a temperature difference, and so there is heat transfer accompanied with it, and therefore there is irreversibility. So the problem is irreversible for two reasons, at least as we see it. We ignore whatever that friction that might be there. We don't talk about it, but at least these 2 points are two good reasons for irreversibilities that might be present. So the second law, the simplified version of the second law, is M2S2 minus M1S1 equals MISI and plus all the entropy generated through this process. Now, let's go through these equations one by one. And as we start with the mass conservation equation. This is mass conservation, and let's see what we can do with this first equation. What we know in this equation is M1. N1 we don't know M2 or Mi. If we know one, we would learn the other. And M2 is something that we said that we don't know for the final condition. Now, we could write this equation. Always, it's a good practice to remember that we could always write the mass conservation equation as V2 over V2 minus V1 over V1, and that equals Mi. We don't need to do this for the time being, for this present the problem, because we know the initial mass. But at least this is a substitution that we can easily do, and often it helps us. And as you see, for the um, final mass, it will help us. So we could write this one, and we could change for V2. We replace V2 from the perfect gas law. It would be V2 times P divided by RT2. You see, I've replaced a specific volume from the perfect gas law with temperature and pressure. M1 is known, so we keep it as it is, and that equals Mi, which is the mass that has entered our control volume. Putting numbers into these values in this equation, it would be 0.6, which is the final mass, times the final pressure, which is 282.8, and divided by RT2, which is 0.287 times T2, which we don't know. Remember that M2 and T2 are the two unknowns for this problem. And this minus M1, which is 1.3, and that equals MI. So we can just simplify this equation, and that would be 591.22 divided by T2 minus 1.3, and that equals MI. This is our first equation that we have um, gained it. We have obtained it from the mass conservation equation. We have one equation, two unknowns. So now we go for the second equation and see what the first law of thermodynamics has to offer. So for the first law, we shall replace values for this equation, and for M2 we know this value, so and we have simplified it to this one. So I will just put it straight from this equation. M2 is 591.22 divided by T2 times U2, which is CV0 T2, minus M1, which is 1.3, U1, which is CV0 T1, and that equals Mi, which is just these two terms, 591.22 divided by T2 minus 1.3 times Hi, which is CP0 Ti. Look, here it was U, so it was CV0 T, and here it was H, so it is CP0 T, and minus W. It seems that we have a lot of knowledge in this equation. We know a lot of values. The only value that we have to calculate it, and it's very simple to calculate, is work. And this is what we should do in our next video. Cheers.